Okay, it's time to put these ions to good use, time to put them to work. Do you remember our ions from last time? Cations, which have developed a positive charge by losing electrons, and anions, which have gained a negative charge by taking on, by gaining electrons. I've got a few examples there for you. Those examples, of course, come from that list of common cations and anions that I mentioned last week. I've popped it in today's additional resources as well. Make sure you grab a copy right now because we're going to need it right throughout the rest of this topic. We're going to build real life everyday ionic compounds, but it's not going to work without that table. So let's start with a nice simple example, one we've sort of touched on from time to time already. We're going to make table salt. We're going to talk through all of the little details as to how table salt, sodium chloride, comes to be what it is. We'll then talk about some nice simple shortcuts that we can take to build hundreds of ionic compounds. So our sodium chloride. Here's our periodic table again. Let's start with sodium. There it is over element number 11 over in group 1, and that means it has one valence electron. There it is. So it really wants to lose that one extra electron so that it will have a stable octet, 8 valence electrons. So it wants to form that positively charged sodium ion, that sodium cation. The problem is, where does that extra electron go? We can't just have electrons floating around in space. It needs somewhere to be. It needs somewhere to go. Back to our periodic table, enter chlorine. Chlorine's in group 7. That means it has 7 valence electrons. Chlorine really wants one extra valence electron so that it can get its stable octet. It wants to form the chloride anion that I've got shown here. Chlorine's problem, where does that extra electron come from? I think you can see how this is all coming together. Here I have sodium. It has one too many electrons, really wants to get rid of it. I have chlorine. It's missing just one electron that it wants, really wants to take one. So sodium gives its electron away, chlorine takes it. We now have a sodium cation and a chloride anion. And did you play with magnets as kids? If you did, you'll know that if you have positive charge and negative charge nearby, they stick, they join together, and this is how an ionic compound is formed. This attraction between positive and negative charge, it's called electrostatic attraction. That's what holds all of these ionic compounds together, and it's a very strong bond. So that is how we make our sodium chloride compound. Now, that's quite a long and drawn out process to go through every time you and I want to build an ionic compound. We can actually use that last concept, the idea that positively charged cations and negatively charged anions will stick together, in conjunction with some other simple observations to build lots of ionic compounds. So, not for the first time I ask you, look around the space you're in, find something that's charged. We agreed last time that the answer to that question is you can't. Things like to be neutrally charged overall. So when we're building ionic compounds, the rules are no different. We want cations and anions to stick together, but they need to stick together in such a ratio that the overall charge, when you add up all of the positive charges and negative charges, adds up to 0, that it's neutral. So if we were making sodium chloride using that principle, we would look at the two ions, the sodium cation and the chloride anion. Sodium's +1, chloride's -1. So they are already of equal magnitude. I simply need one of each to make sure I end up with a neutral compound overall. And there it is, sodium chloride. So this would be the molecular formula, the simplest piece of table salt, of sodium chloride that we can make. Let's try a different salt, let's try a different material. I now want to make the ionic compound out of magnesium cations and chloride anions. When I look at them, magnesium has a charge of +2, while chloride is only -1. Again, when I add these together, it has to add up to 0. The only way that's going to work is if I have an extra chloride anion. That way I've got 2+ from the magnesium and 2 negatives from the chloride. So to build magnesium chloride, I need the 2 chlorides, and we demonstrate it like so. We write Mg for the magnesium, we follow that with Cl for the chloride, and the little 2 at the bottom tells me I want just 2 of the chloride ions. That way our charge is balanced out, it's 0. There we are, sitting in the bowl for you is magnesium chloride, MgCl2. Let's run through a few other examples, try and beat me to the answer. So here I've got some washing soda. Washing soda is sodium carbonate, charge on the sodium ion is +1, charge on the carbonate ion, that's -2. So to make this balance out, I need 2 sodiums for every 1 carbonate ion, so that will be Na2CO3. There's my washing powder, there's my sodium carbonate. Let's try another one, calcium carbonate, or more commonly known, this is just simple chalk that we use on a blackboard. The charge on the cation, the calcium, is +2. The charge on the anion, the carbonate, is -2. The charges match up, so all we need is one of each, one cation and one anion. There it is, calcium carbonate, your chalk. As far as difficult combinations and things go, the list of cations and anions I gave you are either 1+, 2+, and 3+, or 1-, 2-, and 3-. So, as far as being cruel goes, this is the worst combination I can give you. For aluminium oxide, the charge on the aluminium is +3, whereas the charge on the oxide, the oxygen anion, is -2. How do I make those combinations add up? There has to be a common factor. And it turns out that the easiest common factor, if I took 2 aluminium cations, each with a 3+ charge, that would take me up to a total of +6. To balance that out, I need 3 of the oxygen anions, because 3 times -2 is -6. I've got +6, I've got -6, and the total is 0. So 2 aluminiums, 3 oxygens, I would write it like this. That's the most challenging combination of charges, so if you're comfortable with that, the charges won't cause you a problem. I have one more interesting example to discuss, and then we'll move on and finish with some naming. The last example I have here, we're going to make an ionic compound from copper ions and nitrate ions. That beautiful blue salt, that rich blue colour, is very indicative of the presence of copper. We'll see that from time to time. Looking at our ionic compound, I can see that copper is 2+, and then that nitrate ion, NO3, has a single negative charge. So I want copper ions, I want nitrate ions, but more specifically, I want 2 nitrate ions, so I put a 2 afterwards. And I'm pretty sure you can see we have a problem. If you came along and read this, it looks like I've got 32 oxygen atoms. This is clearly a problem, so to help distinguish between that, what chemists do, when we have more than one of these polyatomic ions, we simply put it in brackets. Now we can see quite clearly that I want 1 copper cation and 2 nitrate anions. So that's all we need to do to be able to build hundreds of ionic compounds. Again, if you have a glance at your table of cations and anions, think about all the combinations you have there of different ionic compounds you can make. You can practice that as much as you like in the discussion forum at the end of this topic. Share ideas with people, or just try and build them yourself. One last thing we'll wrap up on before we move away from ionic compounds is naming them. The rules for naming them, particularly if you have that table, is quite simple and straightforward. So here I have 3 examples. When we're naming and when we're writing them, we write the cation first and the anion second. The name of the cation does not change, so this one here I have Ki. K is the symbol for potassium, so that name will stay the same. When my anion is made of just 1 atom, all I do is change the ending of that atom to "ide". So iodine becomes iodide, chlorine becomes chloride. So this ionic material will be called potassium iodide. That's the naming. The rules are quite similar for these other compounds where I have polyatomic ions, but when it comes to naming those polyatomic ions, you can use that table that I've given you. So in this case, the second one, the Na is for sodium, and NO3, if you look up your table, you'll find that's called nitrate. This is sodium nitrate. The last one, Li, is for lithium. That name stays the same, and the CO3, check your table, that's called carbonate. So lithium carbonate. Right, huge topic for us today. We can now build ionic compounds, as many and any that we like. We can do it just by knowing the common charges on cations and anions. Just make sure that the charge that comes from your positively charged cations matches with the charge that comes from your negatively charged anions. Provided they add up to 0, you've built yourself an ionic compound. Alright, that'll do for ionic compounds. In the next few topics, we'll start looking at the other half. We'll start looking at covalent compounds.